Introduction to Quantum Information Processing. Welcome to Lecture 7. In this lecture, we are going to investigate a black box problem called Simon's problem. For this problem, there is an exponential difference between the probabilistic classical query cost and the quantum cost. Also, the quantum algorithm for this problem introduces some powerful algorithmic techniques in a simple form. Simon's problem is a slightly more complicated black box problem than those that we've seen up till now, involving functions from n bits to n bits. It's interesting for two reasons. The first reason is that it's very hard classically, requiring exponentially many queries even for probabilistic algorithms that can err with constant probability, say 1/2. However, there is a quantum algorithm that solves it with a polynomial number of queries, so it improves on the progression of black box problems that we started last lecture. The second reason why it's interesting is that it introduces a technique that transcends the black box model. When looked at in the right way, the ideas introduced in Simon's algorithm lead naturally to Shor's algorithm for the discrete log problem, which is not a black box problem. Shor discovered his algorithms for discrete log and factoring soon after seeing Simon's algorithm, and in his paper, he acknowledges that he was inspired by Simon's algorithm. Okay, now I'm going to show you what Simon's problem is. The problem concerns functions from n bits to n bits that are 2-to-1 functions, which means that for every point in the range, there are exactly 2 pre-images. In other words, for every value that the function attains, there are exactly 2 points A and B that both map to that value. We call such a pair of points a colliding pair. If A is not equal to B and f of A equals f of B, then A and B are a colliding pair. Now, there's a special property that some 2-to-1 functions have that we'll call the Simon property. The property is that there exists an n-bit string R such that the following holds. For every colliding pair AB, the XOR of A and B is R. By the XOR between two n-bit binary strings, we mean the bitwise XOR. That is, you take the XOR of the first bit of A with the first bit of B, then you take the XOR of the second bit of A with the second bit of B, and so on. Let's look at an example. Here's a 2-to-1 function from 3 bits to 3 bits. I've color-coded the colliding pairs. For example, if you look at the 2 green points in the domain, 0, 0, 0 and 1, 0, 1, you can see that f maps both of these points to 0, 1, 1, and those are the only points that are mapped to 0, 1, 1. So the 2 green points are a colliding pair. Also, the 2 red points, 0, 1, 1 and 1, 1, 0 are a colliding pair, both mapping to 0, 1, 0. And there is a turquoise colliding pair and a purple colliding pair. Okay, so this is a 2-to-1 function. But it also has the additional Simon property. If you take any colliding pair AB and take the bitwise XOR of A and B, you will always get the same 3-bit string. Can you see what that 3-bit string is in this example? Please pause the video and think about this. Okay, did you get 101? If you pick any color and take the bitwise XOR of the 2 strings of that color, you'll get 101. For example, for the red pair, you take the bitwise XOR of 0, 1, 1 and 1, 1, 0, which is 101. Note that For an arbitrary 2-to-1 function, the bitwise XORs can be different for different colliding pairs. So the 2-to-1 functions that satisfy the Simon property are special ones, for which these bitwise XORs are always the same. Now we can define Simon's problem. What you are given is a black box for a function from n bits to n bits, and it is promised that this function is 2-to-1 and satisfies the Simon property. But you don't know anything else about the function. You don't know what the colliding pairs are, and you don't know what the value of r is. Your goal is to find the value of r. In the example, it would be 101. For a general function from n bits to n bits that satisfies the Simon property, r could potentially be any non-zero n-bit string. Let's try to think about how hard this black box problem is. In the example, we could find r by taking the bitwise XOR of any colliding pair. So, once we have a colliding pair, it's easy to find r. Therefore, one way to solve this is to find a colliding pair. But notice that any two n-bit strings could be a colliding pair for some r. So, if we make a query at some point a, we learn the value of f of a. But we have no idea for which b, a and b are a colliding pair. Here's an example of a classical algorithm for Simon's problem. If we have a budget of m queries, query f at m random points and then check if there is a collision among them. If any two are a colliding pair, then their bitwise XOR is the answer r. If there are no collisions, then the algorithm is out of luck. In that case, it fails to find r. How large should m be set to so that the probability of a collision is at least 3/4? There are 2 to the m points in the domain, and each pair of queries will collide with probability 1/2 to the n. Since there are around m squared pairs, the expected number of collisions is roughly m squared times 2 to the minus n. Setting m to be the square root of 2 to the n suffices to make this expectation a constant. You may recognize the so-called birthday paradox, where you consider what the chances are that there are two people in a group of, say, 23 people who have the same birthday. It's 50%, assuming that people's birthdays are uniformly distributed. So there's a classical algorithm that solves this with order square root of 2 to the n queries. It's better than querying f everywhere, which would cost 2 to the n queries. But the square root, it just amounts to a reduction by a factor of 2 in the exponent. It's still exponentially many queries. Moreover, there does not exist a more efficient classical algorithm. How do we know that? We cannot deduce this simply based on the fact that this is the best algorithm that we could come up with. How can we be sure that there isn't a clever trick that we haven't discovered? Also, notice that f is not an arbitrary 2-to-1 function. It is a 2-to-1 function with the special Simon property, which gives it a very special structure. So it's conceivable that a classical algorithm could somehow take advantage of that structure. The stated theorem is true, but it does require a proof. The proof is not as trivial as the argument that 2 queries are needed for Deutsch's problem, or that 3 queries are needed for the 1 out of 4 search problem. It requires a more careful argument. If you're interested in seeing the proof, there's a 2-page write-up posted on the course website. The proof isn't particularly hard, but it does require some setup and I don't want to get into that in this lecture. Instead, I'd like to show you Simon's quantum algorithm for this problem. Before looking at the algorithm, there are some preliminaries about a way of viewing the set of n-bit binary strings that I want to explain. To start with, let's look at what performing a Hadamard transform on each of n qubits does to the computational basis states. If all the qubits start in state ket 0, then the result is a tensor product of n ket plus states, which multiplies out to a uniformly weighted superposition of all the n-qubit computational basis states. But what about applying this to other computational basis states? It turns out that there's this nice expression for applying an n-fold tensor product of Hadamards to computational basis state ket A. It's a uniform superposition of the computational basis states, but with certain phases. The phase of the ket B term in the superposition is -1 to the A dot B, where A dot B is this expression, which is a dot product of the n-bit strings in mod 2 arithmetic. For example, H tensor H is this matrix. Look at the entry in the red box. It is in row 1, 0 and column 0, 1. The dot product of 1, 0 and 0, 1 is 0. So the entry is -1 to the 0, which is +1. Now look at the entry in this red box, which is in row 1, 0 and column 1, 0. The dot product of 1, 0 and 1, 0 is 1. So the entry is -1 to the 1, which is -1. Now let's prove the theorem. It will be an easy proof. For a single qubit in state ket A, applying H yields the plus state or the minus state. And that can be written succinctly like this. We can write this even more succinctly as a sum, like so. Now, for n qubits in states ket A1, ket A2, and so on up to ket AN, we insert the above expression for each output qubit like this. We can multiply out the sum as follows. And then we can gather together the exponents of -1 into one exponent. What matters in the exponent of -1 is just whether it's an even number or an odd number. So we can take the sum in the exponent in mod 2 arithmetic. And that proves the theorem. So we have a nice expression for applying the n-fold tensor product of the Hadamard on basis states. In particular, notice how the dot product of two n-bit strings arises. Now, let's think of the set 0, 1 to the n, the set of all n-bit strings. It's often useful to associate these strings with mathematical objects, such as the integers 1 to up to 2 to the n minus 1. But we can also think of the set as an n-dimensional vector space, where the components of each vector are 0 and 1, and the arithmetic is modulo 2. This is different from a vector space over the real numbers or over the complex numbers, but the set 0, 1 with addition and multiplication modulo 2, which is often denoted as Z with subscript 2, is a field, meaning that it shares some of the key structural properties that the real and complex numbers have. I won't go into the details of these properties here, but it's perfectly valid to have a vector space over a finite field like Z2. The notions of subspace, dimension, and linear independence make perfect sense over these vector spaces. And this brings us to that dot product expression that arose in the n-fold tensor product of the Hadamard. For vector spaces over the reals and complex numbers, the dot product is an inner product. and has useful properties. Two vectors are orthogonal if and only if their inner product is 0. Technically, the dot product in our finite field scenario is not an inner product. An inner product has to have the property that for any vector A dot A equals 0 if and only if A is the 0 vector. In our finite vector space, there are non-zero binary strings whose inner products with themselves are 0. Can you think of one? Yes, any binary string with an even number of ones has a dot product 0 with itself. Nevertheless, this dot product does have some nice properties. For example, the space can be decomposed into orthogonal subspaces whose dimensions add up to n. Two spaces are deemed orthogonal if every point in one has dot product 0 with every point in the other. Here is a schematic picture of a decomposition of 0, 1 to the 3, the set of 3-bit strings, decomposed into a one-dimensional space and an orthogonal two-dimensional space. Of course, the picture is really applicable to vector spaces over the reals, not the finite field Z2. So it should just be seen as an intuitive guide rather than a literal depiction. A word of caution here is that for n-qubit systems, there are two spaces in play. One space is the n-dimensional discrete vector space of n-bit strings over a finite field. This is associated with the labels of the computational basis states. The other space is the 2 to the n dimensional Hilbert space spanned by the 2 to the n computational basis states. Do not conflate these different spaces. For example, the n-bit string of all zeros is the 0 vector in the finite vector space, but the ket, whose label is the n-bit binary string of zeros, lives in the Hilbert space, and it's definitely not the 0 vector. It's a quantum state, which is a vector of length 1. With all this in mind about the vector space structure of the n-bit binary strings, let's now turn to Simon's quantum algorithm. The F queries look like this. The input to F is n bits and the output is n bits. So a query acts on 2 n bits. In the computational basis, F of the first n bits is XORed onto the last n bits. That XOR is a bitwise XOR. B is n bits and F of A is n bits. With queries like this, it's not so clear how we could query in the phase, as we did with all the quantum algorithms in the previous lecture. We'll start out differently, with the target qubits just in state ket 0. But we will put the inputs to F into a uniform superposition of the n-bit strings, and then we'll perform an F query. What's the output state of this circuit? You may pause the video to think about this. Okay, so the state right after the query is a uniform superposition of basis states of the form ket A tensor ket F of A. Let's think about this state. It's sometimes said that what makes quantum computers so powerful is that they can actually perform several computations at the same time. This state was obtained by making just one single query, but it looks like it contains information about all of the values of the function f. But this view is misleading. It's not possible to extract more than one value of the function from this state. In particular, if we measure this state in the computational basis, then what we end up with is just one pair, A and F of A, where A is sampled from the uniform distribution. And you don't need any quantum devices to generate such a sample. You could just flip a coin n times to get a random A and then perform one query to get f of that A. So, how should we think about quantum algorithms? With a state like this, rather than measuring in the computational basis, we can instead, via a unitary operation, measure with respect to another basis. In some cases, for a well-chosen basis, we can acquire information about some global property of the function f instead of the value of f at some specific point. Let's try to find a useful measurement basis for this case, where f is a function satisfying the Simon property. The inputs to the function partition into colliding pairs, where we can look at our example for reference. Let's define a set T so as to consist of one element from each colliding pair. So, in the example, we take one of the two green points, one of the two turquoise points, one of the two purple points, and one of the two red points. Which one we choose won't matter. The point is that there exists such a set T. Now, notice that for each element A in T, the other element of the colliding pair is A XOR R. We don't know what R is. That's what we're trying to find by the algorithm. But we know that F satisfies the Simon property and that there exists an associated R. Recall that in the example, the R is the string 101. Therefore, if we take all the elements of T and combine this set with all the elements of T XORed by R, then we get all the n-bit strings. Therefore, we can rewrite the output state this way, where we are only summing over the elements of T, but for each A in T, we include two terms, one for A and one for A XOR R. So, writing the sum this way includes all the terms in the original sum. Now, since F satisfies the Simon property with the associated R, for each A we have that f of A equals f of A XOR R. That's exactly what the Simon property says. So we can write the sum like this. Here's the state after the query again. Now, suppose that we now measure the last n qubits in the computational basis. Then the state of the last n qubits collapses to some value f of A, and the residual state of the first n qubits is a uniform superposition of the pre-images of that value. That is, the state of the first n qubits is a superposition of ket A and ket A XOR R for a random A. There's a 1 over root 2 normalization that I'm leaving out here. Now, what can we do with this state? If we could somehow get both ket A and ket A XOR R, then we could deduce the value of R. But we can only measure the state once, after which it collapses. If we measure in the computational basis now, then we just get either A or A XOR R, neither of which is sufficient to extract the value of R. If we measure in the computational basis, then it's like we first randomly choose a color. That's what happens when we measure the last n qubits. And then we randomly choose one of the two elements of that color. That's what happens when we measure the first n qubits. So the net effect of all this is that we just get a random n-bit string, which is devoid of any information about the structure of F. So if we want to make progress, then we definitely don't want to measure the first n qubits in the computational basis. What happens if, instead of measuring in the computational basis, we apply a Hadamard transform to each of the n qubits? Let's calculate the resulting state. We apply the n-fold tensor product of H to the state, which by definition gives this state. Notice that we're using the theorem about what tensor products of Hadamards do to computational basis states. We take a uniform superposition of the computational basis states with phase set to -1 to the a dot b for the case of ket A, and -1 to the a XOR r dot b for the case of ket A XOR r. We can rewrite the phase -1 to the a XOR r dot b as the product of -1 to the a dot b and -1 to the r dot b. This permits us to factor out the -1 to the a dot b, which appeared in both terms. Now, let's think about what happens if we measure this state in the computational basis. Here's the state again with the normalization added. To figure out the probability of any particular outcome B, we need to look at the amplitude associated with ket B. Since the probability is the absolute value of the amplitude squared, the -1 to the a dot b has no bearing. But look at what's in the parentheses. For some values of b, it's 0. And for some values of b, it's 2. If the bit r dot b is 1, then the expression is 1 plus -1, which equals 0. If the bit r dot b is 0, then the expression is 1 plus 1, which equals 2. Therefore, only the values b where r dot b equals 0 can arise. Otherwise, the probability of the outcome is 0. In our discrete vector space, those are the strings b that are orthogonal to r. And among all the strings b that are orthogonal to r, we get a uniformly random sample. This does not produce enough information for us to deduce r, but it provides us with partial information about the bits of r. What we can do now is repeat this whole process n times. Each time, we get another independent random sample from the space of all strings that are orthogonal to r. That costs n queries to the function f. Now, r is a solution to this system of linear equations where each row is one of the random strings b that we get from one of the runs. We can solve the system using Gaussian elimination to calculate r. For this to work, the matrix of b's should have rank n-1, the maximum rank possible in this context. Then there will be a unique non-zero solution r. This is not guaranteed to happen. We could be very unlucky and get the 0 string for each run, in which case we can deduce nothing about r. But that's unlikely. It's not so hard to prove that, with probability at least a quarter, the rank will be n-1, in which case there is a unique non-zero solution to the system of equations, which then must be r. I'll leave it as an exercise for you to show that the rank is n-1 with probability at least 1/4. So we now have a quantum algorithm that makes n queries in all and succeeds in finding r with probability 1/4. By repeating this whole procedure 5 times, we can get the failure probability below 1/4, because 3/4 to the power 5 is less than 1/4. In conclusion, order square root 2 to the n queries are necessary for any classical algorithm to attain success probability 3/4, whereas order n queries are sufficient for a quantum algorithm to attain success probability 3/4. Now, what should we make of Simon's problem and Simon's algorithm? It's a black box problem that was specially designed to be very hard for probabilistic classical algorithms and easy for quantum algorithms, thereby improving on previous classical versus quantum query cost separations. But it doesn't immediately look like a problem that one would care about in the real world. When this work first came out, people were wondering what to make of it. Although it provided the strong query cost separation, it looked like a contrived problem. Moreover, a contrived black box problem, which is not really a conventional computing problem involving input data. This may be one's first impression, but there's actually more to it than that. Let's look at the Simon property for all A, f of A equals f of A XOR R. This is kind of like a periodicity property of a function, which would be written as for all A, f of A equals f of A plus R. And periodic functions arise in many natural contexts. We'll soon see that variations of Simon's problem in this direction are very fruitful. Okay, let's end this lecture now.